Whether there's a logarithmic relationship between the height of a tree and its number of nodes depends upon how close a tree is to being full. Let's explore one way to make that determination, which is to check whether a tree is balanced. Before we can define what it means for a binary tree to be balanced, we must begin with a definition of a balance factor. The balance factor of a node is the difference between the height of the left subtree and the right subtree. Let's consider the two extremes to help explain this concept. Full trees are the most balanced binary trees. In a full tree, all the nodes have a balance factor of 0. At the other extreme are Fibonacci trees, which represent the sparsest trees that are still balanced. The maximum balance factor of all the nodes in a tree is a measure of how out of balance a tree is. Trees that have degenerated into lists are the most unbalanced trees. In such trees, the balance factor can be as large as the number of nodes in the tree. Now we're ready to define what it means for a binary tree to be height balanced. As we did with binary search trees, we will provide both an iterative and recursive definition. First, the iterative definition. A balanced binary tree is a binary tree in which the value in each node has a balance factor whose absolute value is less than or equal to 1. Notice that if the height of the left subtree is greater than the right, the balance factor will be negative. But what is significant is its magnitude, not its sign. Next, the recursive definition. As with every recursive definition, we need a base case, which is an empty tree, and every empty tree is height balanced. If the tree is not empty, there are two required properties. The root node must have a balance factor whose absolute value is less than or equal to 1, and the recursive part of the definition states that both subtrees must be height balanced. As was true when we provided two definitions of a binary search tree, these two definitions are also equivalent. So now let's look at some examples of trees and their balance factors, and also whether the tree is height balanced. So we'll start asking what the balance factors are. Notice already that we're going to have some high balance factors, in particular right here, also right there. So if we look at the balance factors, we'll see that this has a balance factor of -3. This one has a balance factor of -2. So then if I ask the question, is this a height balanced tree? It's going to identify for me some of the nodes that are out of balance. Okay, let's look at one more. This one is also going to be out of balance. In particular, we can see that that node is not going to have a balance factor within the range -1 to +1. So if we look at the balance factors, we see that that's -2. If we ask whether the tree is height balanced, of course, it's going to tell us no, and it's going to identify a number of the nodes that are out of balance. All right, so for a binary tree to be height balanced, all of the nodes have to have a balance factor between -1 and +1. So let's examine some pictures of the two extremes, full and Fibonacci trees. In a full tree, every node has a balance factor of 0, which includes all those nodes that are not leaf nodes. In a Fibonacci tree, the leaf nodes have a balance factor of 0, as leaf nodes always do, but the other nodes all have a balance factor of 1. So that makes full trees the fullest balanced trees, and Fibonacci trees the sparsest that are still height balanced. Finally, we discuss binary search trees that are self-rebalancing. Recall that to ensure that the height is logarithmically related to the number of nodes, a binary search tree must be balanced. Depending upon the order in which the elements are added, Adding an element can cause the tree to become unbalanced. There are several types of binary search trees that are rebalanced when such an addition causes them to go out of balance. The first type are AVL trees. These trees are always kept strictly height balanced. They are named after Adelson Velsey and Landis, who originally described them. The second type are red-black trees. These trees are kept balanced, but not strictly height balanced. They're used by the Java Collection Framework classes TreeSet and TreeMap. The third kind are splay trees. They have an additional property that recently accessed elements can be accessed quickly.